Today we'll talk about examples in differential amplifiers for the last part. Example 10.25, it is talking about the telescopic parasitic resistance, and as we did before, here this node can be assumed as a virtual ground. Then you can use half circuit. To use half the circuits, you have divide this R1 into two different resistors, such as R, let's say 2, and R3. Of course, R2 is equal to R3, and that one is half of R1. Then the center can be assumed as a virtual ground. So by using the half circuit on the left hand side, you can convert it into this figure. So you assume that this DC is AC ground, and we add all the AC ground parts like that. So the GM for, let's say, the voltage gain for the system is minus. So numerator becomes all the resistance from the output to AC ground. We have two different passes. So let's say this is ROP and this is RON. And let's define RON in this case. Then this is in parallel with ROP. And ROP is pretty much the same as what you did for RON. So from now on, by cascade connections, the resistance becomes larger. So RO3 plus 1 plus GM3 times RO3 close parenthesis, then it is multiplied by RO1 in parallel with R pi 3. Then of course this is a value for RON, and it is parallelly connected to ROP. I don't know why this horizontal line keep comes. It bothers me a lot. The denominator is simply from the source side, it's from the emitter side to the input. That means that it is simply 1 over GM1. So that's the reason you got this answer. And by assuming that GM times RO is much larger than 1, you can come up with this result. And also, we have to make sure that RO3 can be much smaller than these values. For example 10.26, it's pretty much the same as what we did before, and the above ideal current source can be assumed as a virtual ground, and you just cut it half. So half circuit can be considered as a left-hand side. There's no problem if you consider the circuit on the right, but in general, we are considering the positive terminals for the input. So for define the voltage gain, we have to tell what is RON and what is ROP. And ROP, the way that we obtain ROP is the same as we obtain RON. So let's do it one. Why don't we choose RON? Then RON is by cascade connection RO3 plus 1 plus GM3 times RO3 times R01. So as you can see here, this answer is right up here. And ROP, because R01 is connected in parallel to M5, you have to include that one when you're calculating RO5. So let's define it. This is RO5 in parallel with R1. Just that's it. Plus 1 plus GM5 times, let's say use a different parenthesis, RO5 in parallel with R1, close the parenthesis, times RO7. So finally, the voltage gain is simply ROP divided by RON, and you divide this value to 1 over GM1, then you can come up with this result. Of course, we have minus sign for common source amplifier. And let's talk about the gain for a common mode to differential. So by having non-ideal tail current, which means that ideally it should be a current source like that one, but we form this current sensor into this kind of configurations. So even though we want to make a high output impedance for this kind of current source, it may not be that high. So that actually the RO3, R output 3 affect to common mode to differential gain. Actually, if common mode to differential gain is equal to 0, that's the ideal case. Even though there are some common mode variations, and that means that in differential point of view, there is no difference. So we already defined that our output 3 is given by RO3, the same way that we obtain output impedance by having cascade connection, plus 1 plus GM3 RO3 times R1 in parallel with R pi 3, like that. Then as you did for the class, we can simply get voltage gain to common mode to differential mode is given by, if there is resistance variations, by delta RC, that is simply given by delta RC time over 2 times the output impedance of the tail current source, which is R output 3 time plus 1 over GM1. You don't need to remember this equation. Just write it down. For the exam, just write it down, and if you want to use this one, that'll be much better, just rather than memorizing whole equations, because it may vary depending upon the circuit. So finally, we have differential pair, and this is the simple connections for diode connected circuit like that. So we have, as you can see here, we have 1 over GM, which is in parallel with its output impedance, RO3. Okay, that's the reason you got that answer. Okay, then let's remove it. So it is asking you to finding out the voltage at the node A. Then it's simply by Ohm's law, the current times resistance will be VA. So VA, if this is I, simply I times RO3 in parallel with 1/GM3. So let's find I. For finding I, you have to start from the input and output relation. You have input, positive input, and the output. So let's use it. By KCL, the outgoing current is the same as the sum of incoming currents. So I is simply given by, because the current direction is in opposite, we have minus sign V output over RO4 in here, minus we have another current path through M4, which is given by GM4 times VA. So if you put this value into the I over here, you can come up with this result. Then assuming that RO3 is much larger than 1/GM3, you can just cancel it out. Then as long as GM4 is pretty much close to GM3, let's assume that just they are the same. Then it's simply given by minus V output over RO4 times 1/GM3 plus GM4 GM3 times VA. Cancels out because it's 1. Then if you put this VA on the left hand side, 2 times VA equal to minus V output over GM3 times RO4. That's the reason we got this answer. Thank you.